Hi, my name is Reagan Shield, and I'm here with my partners Will and Min, and this is our Chapter 1 Introduction to Monte Carlo, Presentation number 2. Alright, discuss what it means to evaluate an integral. Well, a definite integral is a function closely related to the antiderivative and indefinite integral of a function. The main difference between the two is that an indefinite integral, if it exists, is a real number value, while the later two represent an infinite number of functions that differ only by a constant. To integrate is to combine separate sections or entities into a whole. So here I have an integral. F of x dx is called a definite integral of f of x from a to b. The numbers a and b are known as the lower and upper limits of the integral. You would then evaluate the integral of f of x the normal way, and then to deal with the definite integral, you would subtract the value of the upper limit b from the value of the lower limit a. The difference between these limits gives you the value of the definite integral. Integration can be used to find areas, volumes, and central points, and many other useful things, but it is most often used to find the area under the graph of a function.
Hi, my name is Ming, and so on this slide I will answer the question, why do we need to simulate data point to find the area? So the first thing, that there will be hard problem like integral is impossible to integrate, and the second is that the useful of large dimensional is very useful, so large higher dimensional problems, and also the complexity of any definite integral going to affect how we do the Monte Carlo estimations. All right, so here is the concept of expectation in Monte Carlo integrations. So Monte Carlo is about, will invoke the law of large number to approximate expectations, and after factoring out any distribution that have an area of 1, then we'll be left with the remaining element. The expectation will be the mean of the area of the random variable generation that we randomly create. And so to answer the question, what is the integral estimation in Monte Carlo integration? So first is it's used when evaluate any definite integral. And also in Monte Carlo integrations, integral estimation will be done by sampling a bunch of variable from any distribution that had area of 1, like normal distribution or uniform distribution. Then we calculate value by plug into the integral, and after that we would take the average of that to get the estimation of the Monte Carlo integration.
Alright, so now I'm going to talk about an important statement. So we have a statement that says we can estimate the value of any integrand no matter how complex the integrand is. And this statement is really important because it reveals that we can at least get an answer that is in the ballpark of the actual value when evaluating integrals. As we've seen in our class, many integration problems that are either unsolvable or extremely difficult to solve can be solved using Monte Carlo integration. And this technique uses random numbers to solve integrals. And we'll get into a little bit of that as the presentation continues. So now let's talk about the relationship among integrations, probability densities, and fissionable materials. So when looking at integrations, probability densities, and fissionable materials, we can make an observation, and that is, for each of these topics, we're looking at values under a curve. For integrations, we often look at areas and volumes under a curve. For probability densities, we often look at experimental occurrences as percentages under a curve. And for fissionable materials, we look at thermal neutron fission values under a curve. Now we'll look at Monte Carlo and complex problems. So as previously mentioned, Monte Carlo can be used to solve those either unsolvable or extremely difficult complex functions. By using random numbers, Monte Carlo evaluates complex problems by randomly evaluating different points of a function. The expectation or mean is then used to find the solution. So complex problems and the mathematics behind the yields of fissionable materials have a lot in common. the yields of fissionable materials can be charted under a curve. Because the functions of the yields behave in a similar way to other complex functions, the mathematics and the way to solve for energy values remains the same. So here we have a MATLAB code, and we have closed form comparison and the Monte Carlo method. And as we will see in this demonstration, we can look at the two and compare the values. So here are our two MATLAB codes, and if we go ahead and run this, we can see that our integration for the closed form for comparison is 6.2911, and the mu for our Monte Carlo method is 6.2912. And these values are extremely close, and that just shows how our Monte Carlo method works compared to the closed form method. Now obviously the integral is able to be solved in closed form, which shows that it's not exactly an unsolvable or extremely difficult problem to solve, but as we get to more complex problems we can't solve using the closed form, Monte Carlo will be used. But for this problem we just wanted to show that Monte Carlo will get you the same answer as closed form. So going back to our PowerPoint, here are our references that we used for this PowerPoint presentation. Thanks for listening.